Let's see, what if more than one inductors are connected in series. That is, let's say this is the first inductor, this is the second, this is the third inductor. So let's say this is L1, this is L2 and this is L3. If a current I passes through these three, because they are in series, same current will pass through them. And let's say the voltage that we have applied is actually V. Okay, so this is the circuit arrangement. Then what is, if you take KVL, this will be minus V will be equal to L1 di by dt, not y, minus V equal to, not equal to, minus V plus L di by dt plus L2 di by dt and plus L3 di by dt. So we can write V is equal to, okay, so V is equal to this, if this is V1, if this is V2 and if this is V3. So our V is equal to V1 plus V2 plus V3. So V1 is L1 di by dt, V2 is L2 di by dt and V3 is L3 di by dt. Now you can write it as L1 plus L2 plus L3 di by dt, because di by dt is common. So what effectively do we get? We can replace these three inductors by a single inductor whose inductance is, the equivalent inductance is L1 plus L2 plus L3. Okay, this is what we get. So we can say L equivalent is nothing but Li, I equal to 1 to N. Okay, so this is the equation for inductors in series. Clear? Now what if we have some inductors connected in parallel? This is first inductor, this is second inductor. We had taken three inductors there, so we will take three inductors here, and let's say we connected to a current source. So let this current be Is. So this is I1, this is I2 and this is I3. From KCL, you know, Is will be equal to I1 plus I2 plus I3. Let this be L1, L2 and L3. So for inductor, you know, current is 1 by L, then V dt, from where? From start to end. Let's say our starting point is T0, T2, plus we have initial condition, the current that is present in the inductor before connecting to this circuit. Okay, so what we can do, we can from here we know Is is actually equal to 1 by L, T0 to T. V is constant for all the three, so V dt, this is for L1. Then we have for 1 by L2, same thing, T0 to T, V dt plus 1 by L3, T0 to T, V dt, and then we have initial conditions for 1, 2 and 3, that is I1, let's say T0 plus I2 T0 and I3 T0. Okay, so we can combine these all three as, let's say, IT0. So this is the initial condition. Now what we get from here, we get this is equal to 1 by L1 plus 1 by L2 plus 1 by L3 into T0 to Tv dt, and then we have the initial condition. Okay, so the equivalent inductances when we have connected in parallel, what is the equivalent inductance? It is equal to 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3, or we can say that 1 by L equivalent is basically equal to I equal to 1 to N 1 by Li. Okay, so this is inductors in parallel. Now let's see capacitors. Capacitors when they are in parallel. I am using 2 capacitors only. We had used 3 inductors. The answer will be same whether you use 2 or 3. So this is the current source we apply to C1 and C2. This is I1 and this is I2. Okay. We know two things. I is C dV by dt in case of capacitors, and the second thing is from KCL Is is equal to I1 plus I2. And what is I1? It is C1 dV by dt plus C2 dV by dt. Why same voltage? Because the voltage is same across these all. So this is C1 dV by dt and C2 dV by dt. From here we get C1 plus C2 dV by dt. Therefore, a very important thing that we learned is when we have capacitors in parallel, you have actually the equivalent capacitance will be addition of this. This is in contrast to what we have learned for resistors and inductors. So you can say C equivalent is if you have more than 2 capacitors, this is Ci I equal to 1 to n summation C1, C2, C3, C plus C4 plus C5. So this is for capacitors in parallel. Now let's see what we know. We know that V is equal to 1 by C I dt plus initial condition. Okay. So this we will use when capacitors are connected in series. See how. Let's say this is our circuit. This is the first capacitor, this is the second capacitor, and we have connected it to a voltage source V. So this is V1, this is V2. Let the current be I flowing in this circuit. Okay. So what do we get? V will be equal to V1 plus V2. And what is V1? V1 is 1 by C1. Let's say this is C1, this is C2. I dt, because current is common from, let's say we have started from T0 to T, plus V1 0 plus the initial condition. And secondly, 1 plus C2, T0 to T, I dt, and the initial condition V2 0 plus. Or we can write it like this: 1 by C1 plus 1 by C2, T0 to T, I dt, plus let's say this is the initial condition combined. So effectively what we get in case of series capacitors, when capacitors are in series, the equivalent capacitance will be this 1 by C1 plus 1 by C2 plus 1 by C3 and so on, or we can write 1 by C equivalent will be equal to 1 by Ci summation I equal to 1 to n. Okay. So now we have seen resistors in series and parallel, inductors in series and parallel, and capacitors in series and parallel. These things you should keep in mind. Okay, let's see how we find equivalent capacitance. We know when capacitors are in series, the equivalent capacitance is like this. If we have two capacitors, 1 by C1 and C2, therefore we can say that C equivalent is C1 into C2 by C1 plus C2. This is when capacitors are in series, and when capacitors are in parallel like this, C and C, let's say C1 and C2, the equivalent capacitance is C1 plus C2. Equivalent capacitance means in place of this you can have this capacitance, which is C equivalent. Okay, so let's find out the equivalent capacitors of some combination of capacitors. So see, these are in parallel. So from here to here we can replace by an equivalent capacitance that is equal to C1 plus C2, because these two are in parallel, and then these two are in series. See, C3. So now C1 plus C2 and C1 C3, these two are in series. So the equivalent capacitance will be C1 plus C2 into C3 by adding the two, that is this. Okay. So this whole combination of capacitors can be replaced by a single capacitor, which is this C equivalent. If this was A and B, this is A, B. This is the meaning. Okay. Now similarly, let's see. If this node is A, this node is B. We have these two in series. So when two are in series, how to find, let's say C equivalent to 1. These two. So what, 2C into 2C and then 2C plus 2C, that is 4C. So what do we get? C cancel, 2, 2, 2 and then 2. So what do we get? C. So now what we have? We have like this, one capacitor and here one capacitor, that is C here, C here. Now C and C are in parallel. So the equivalent capacitance will be, this equivalent will be this C plus C, that is 2C. Okay, clear? Now let's see some more circuits. Third one, see, these two are in parallel. Therefore, what we can do, we can replace it by an equivalent capacitance, that is this plus this, that is, this is 3C. Now in the lower half we have 2C plus 2C in parallel. So 2C and 2C in parallel means 2C into 2C plus 2C plus 2C, 4C, that is, you get only C. Remember, when you have same capacitors, when they are in parallel, the equivalent capacitor will be half of it, that is, equivalent will be this only. Okay, so this reduces to this. Now these two are in parallel, so this will be this plus this, that is 4C. Okay, so the equivalent capacitance is 4C. This one is typical. Why? Let me explain. Let this node be M and this node be N. Okay, now what I am doing, let's say this is our N node and this is M, node M. This is node A and this is node B. Okay, now we have between A and N 1C. So this is this one, this C we have used. Then between A and M we have the next C. So this is this one. Okay, then this is between M and B, M and B, M and B. So this is this one. Okay, then between M and N, M and N. Okay, and then which one is left? This one, N and B, N and B. So if you redraw this picture, it will be like this. See, if you redraw this picture will be like this. This is the combination. Now you must have heard of Wien bridge. In a Wien bridge, if this by this ratio is equal to this by this ratio, then current doesn't enter this capacitor or whatever impedance you have, a resistor or capacitor or whatever impedance you have. So current won't enter this capacitor. Then what? This will be in parallel and these two will be in series and these two will be in series. Clear? Let me explain this again. This is Wien bridge. In Wien bridge, what happens when this by this ratio 1 is equal to this by this ratio, C by C equal to C by C, then current doesn't enter this path. So you effectively, this is open circuit. Effectively, that is between M and N, this capacitor does not takes any current. Then now what is our figure? These two are in series, that is C and C are in series. So what you will get when C and C are in series? You will get C by 2. So this picture is 1C, that is C by 2, and again here also C by 2. So this is now like this, C by 2, C by 2. And now when these two are in parallel, the equivalent circuit will be C by 2 plus C by 2, that is C. So finally what we get? C. Clear? So now this is fifth question and this is sixth question. Let's say fifth one. Fifth one looks complicated but is very easy. See, these are two nodes. So when these are two nodes, here this is in series, this and this is in series. So C and C are in series here. So in place of this, you can write C and C in series. What is the meaning? C cross C by 2C, that is, you get C by 2. So you have C by 2 here. I'm working on this figure only. Okay, so C and C can be removed like this. This is the equivalent circuit is C by 2. Now you see these two, C and C by 2, these two are now in parallel. See, these two are in parallel. These are the two nodes. So what is, when they are in parallel, they will be added. C plus C by 2, that is 3 by 2C. So instead of this C, now we can write this is actually 3 by 2C. Okay. Now look at this part. These two are in series. See, 2C and 2C. These two are series. If a current starts here, it will go like this and then return. So this 2C and 2C are in series. So when 2C 2C series means single C, that is 2C cross 2C by 4C. See, so now we can replace this by a single C. Now what we have? 3 by 2C and C are in parallel. So the equivalent capacitance will be 3 by 2C plus C, that is 5 by 2C or 2.5C. Okay. So this is how we get this question. Now this question is very good. Sixth one. Why? See, for some time just disconnect this. Okay. And let's see what this figure is. See, again these two, if this point is taken, see here I am redrawing the figure. Okay, let's say this point is M, this point is N, and then this point is P, this is Y. Okay, so what we'll do, we'll take this point is actually not M, this is X only. See, this is X, so this point is X, this is one node. So I am taking this node X. Okay, and then I am taking the other node Y here, this node. Now P I am taking somewhere here, let's say P is here, and then we have N here and we have Y is here. We have only these 2 points. Okay, so let's put N here. First is between X and P, so this is our capacitor C. Then we have between X and N, we have used this C. Then X and N, here we have X. Okay, C. Then we have between X and Y, that is directly putting it like this, let's say. Okay, so X and Y, C, this one. Then N and Y, this one. So we have used this. Now this one, N and P. Okay, so N and P used. Finally this one, P and Y, P here and Y. So our picture is like this. Leave this C, that is leave this C for some time. What you will get? You will get, this is a VN bridge again, the way we saw there. See, this is C by C, the ratio is equal. So what we can do? We can omit this, because this by this is equal to this by this. Now what we get? We get C and C in series. So C and C in series means equivalent will be C and C in series means C by 2. Again C and C in series, equivalent is C by 2. Okay. Now C by 2 and C by 2 in parallel. Let's see this one first and then this one. C by 2 and C by 2 in parallel. So the equivalent will be C by 2 plus C by 2. That is, we'll have this one like this. C by 2 plus C by 2, that is C. Now C and C in parallel. So equivalent will be C plus C, that is 2C. Okay. So the tip is that whenever you find any circuit in which you have this type of configuration, that between two nodes you are getting one impedance and you have impedances like a bridge, you must check out whether it is a Wein bridge. Okay, so we have solved so many questions on capacitors. This way we can solve many. The next thing that I'll tell you is star and delta connection. That should also be kept in mind. Sometimes it's very useful to solve questions, I'm telling you.